Question 1. Collector feedback bias. Figure 1 below show a BJT bias circuit. Calculate base current IB, collector current IC, emitter current IE, and collector to emitter voltage VCE. How to calculate IB? To calculate IB, we can use KVL. So, VCC minus ICRC minus IBRB minus VBE equal to 0. So we can simplify this equation and we can get IB equal to VCC minus VBE divided by RB plus beta RC plus RE. Put the value in this equation and we get the answer 18.08 microampere. Next, how to calculate IC and IE. To calculate IC and IE, we use a formula. The formula is IC equal to beta IB. And after we put the value in this formula, we get 2.17 milliampere. IC is equal to IE, so IE equal to 2.17 milliampere too. How to calculate VCE? To calculate VCE, we use KVL. So, we can get the equation. The first equation is VCC minus ICRC minus VCE minus IERE equal to 0. VCE equal to VCC minus ICRC plus RE. How we get IC bracket RC plus RE? We use this formula because IC and IE is in the same value, so we can factorize. After we factorize, we just get IC bracket RC plus RE. Put the value in this equation and we get VCE equal to 5.58 volts. That's all.
Assalamualaikum warahmatullahi wabarakatuh. My name is Hazwan Hisham and I will explain about simulation of question 1. As you can see here, it's a simple circuit and this is to find the IB, which is 70.2 microampere, IC is 2.95 milliampere, and multimeter 1 is to find the VCE, which is 5.317 volt, and multimeter 2 is to find the current of the R2, which is a 2.968 milliampere.
Question 2. Refer to the circuit in figure 2. Determine the collector current IC, base current IB, emitter current IE, collector to emitter voltage VCE, and collector to base voltage VCB. Given beta DC is equal to 50. To find collector current IC, by using the formula IC is equal to BDC times VCC minus VBE over RB. Substitute the value of BDC, which is 50, times VCC, which is 12, minus VBE, which is 0.7, we got 11.3, divided by RB, which is the value of 240 kilo ohm, and the answer is 2.354 milliampere. To find base current IB, by using KVL, we got the equation of VCC minus IBRB minus VBE equal to 0. From the equation, we can get IB equal to VCC minus VBE over RB. Then, substitute the value of VCC minus VBE, which is VCC 12 volt minus VBE, which is 0.7 volt, over RB, which is 240 kilo ohm. Therefore, we got the answer for IB, which is 47.08 microampere. Next is to find emitter current IE. Since we already have the value of IB and IC, we can use the formula IE is equal to IB plus IC. Substitute the value of IB and IC, which is 47.08 microampere plus 2.354 milliampere. The result for IE is 2.401 times 10 negative 3 ampere, or known as 2.401 milliampere. Next is to find collector to emitter voltage, VCE. By using KVL, we can get the equation of VCC minus ICRC minus VCE equal to 0. From the equation, we get VCE equal to VCC minus ICRC. Substitute the value of VCC, which is 12, minus ICRC, which is 2.354 times 10 negative 3 times 2.2 kilo ohm. We can get 6.82 volt for VCE. Lastly, to find collector to base voltage, VCB. Since we already found the value for VCE and VBE, we can use the formula VCE equal to VCB plus VBE. From the formula, we get VCB equal to VCE minus VBE. Substitute the value of VCE and VBE, we get VCB equal to 6.82 volt minus 0.7 volt. Therefore, we get VCB equal to 6.12 volt.
Alright, moving to the question 2. This is the circuit for the question 2. As you can see here, the IB is a 47.1 microampere, IC is a 5.40 milliampere, IE is a 5.45 milliampere. For the multimeter 1, as you can see here, is to find the VCE, which is a 113.254 millivolt. For the multimeter 2 is to find the VCB, which is a 577.8 millivolt.
Question 3. Voltage divider bias. Figure 3 shows a voltage divider bias circuit for bipolar junction transistor BJT given beta DC equal to 110. First, determine whether the BJT is in condition or not. The second one is by referring to use appropriate method to calculate the collector current IC and collector to emitter voltage VCE. To determine the condition, we use if R in base equal to 10R2 and then the BJT will be in the stiff condition. First, we find R in base. R in base equal to beta DC times RE. We get 110K. Second one, we find 10R2 equal to 150K. So we can conclude that R in base is less than R2. So the BJT is not in stiff condition. The second question is to find IC and VCE. First, we must find VB. VB equal to R2 divided by R1 plus R2 times VCC. We get 2.17 volt. The second one, we must find VE and IE. VE is equal to VB minus VBE. So we get 1.47. And RE is equal to VE divided by RE. We get 1.47 milliampere. Therefore, IC is equal to IE. So IC is equal to 1.47 milliampere. To find VCE, first we must find VC. VC is equal to VCC minus ICRC. So we get 5.766. And to get VCE, we must minus VC with VE, and we get 4.296 volts. That's all. Thank you.
Last question is a question 3. This is a circuit for the question 3. To find the IC is a 1.41 milliampere, and for the multimeter 1 is to find the VCE, which is a 4.466 volt.
Here are the question 1. Here is the value for the calculation and simulation. Based on the calculation and simulation value for IB, IC, IE and VCE is slightly different, but we can see that the value of IC and IE for calculation and simulation is often higher than value of IB. In collector feedback bias, when the value of IC increases, less voltage is applied to the base. Next is question 2. Here is the value for the calculation and simulation. Based on the value of calculation and simulation is distinctive. Based on theory, this is because it is base bias circuits where its circuit is very unstable since its beta changes with temperature and collector current. Last is discussion for question 3. Here is the circuit. Here is the question 3 calculation and simulations value. The value of calculation and simulation is slightly different, but the value is close. Maybe it's because of decimal places. Because in voltage divider bias, the resistor helps to give complete control over the voltage and current that each region receives in the transistor. RE also allows for stability of the gain of the transistor. And that's all from us. Thank you.